Alright, so hi everyone. Today we're going to be doing a lab on conservation of energy. So before we get into the experiments, let's recap some of the ideas that we covered in lecture that deal with energy. So the first thing is, what is energy? Well, energy is a bit of a fluid concept because it can take on so many different forms. But if you really account for all the different forms of energy that exist within whatever system you're studying, you're always going to find that energy is conserved. So what are some of those different forms of energy that we need to know about? Well, the first is kinetic energy. Now, kinetic energy has to do with the motion of an object. So if I throw this ball into the air, we say it has kinetic energy just by virtue of the way it's moving. On the other hand, we have potential energy. And potential energy has to do with position. So if we're talking about gravitational potential energy, that has to do with how high off the ground this ball is. And in particular, if the ball is up here, it has more potential energy than if it's down here. But the point is, potential energy has to do with the position of an object. Okay, so if we take the sum of all the different kinetic energies and all the different potential energies in a given system, then we're going to find that that total is called the mechanical energy of the system. And as long as our system doesn't have any non-conservative forces like friction or like air resistance that are doing work, then mechanical energy is conserved. In other words, the sum of kinetic plus potential is going to be conserved in any system where we don't have non-conservative forces like friction or air resistance that are doing work. All right, now, if we do have those types of non-conservative forces doing work on our system, then mechanical energy can change. So in particular, let's say friction is doing work on a system you're looking at. Well, mechanical energy is going to decrease because friction tends to slow things down. So what we don't want to do is say that the energy has somehow disappeared from the universe altogether. If mechanical energy is decreasing, that is just being transformed into some other type of energy. Okay? And in particular, that type of energy is called internal energy. So internal energy is the energy due to the random motions of the molecules that make up a given system. So the more quickly the molecules are jiggling around, the more internal energy the system has. Okay, if the molecules are jiggling around more slowly, it has less internal energy. And this translates to what we experience as heat. So a system with a lot of internal energy, it'll feel hot to the touch. Something with less internal energy, it feels colder. So when a non-conservative force, like friction, does work on a system, yeah, it does decrease the mechanical energy of that system, but it's really just converting that mechanical energy into internal energy, and we can actually see that it will heat the system up in the process. So those are the ideas I wanted to sort of summarize for you guys today. We're going to be doing an experiment that actually is in two parts. So let's go to the first part of our experiment here today. Okay, so here's the setup for the first experiment. It's fairly straightforward. We have a cart on a track, and at this end of the track, there's a motion detector. The track is also propped up at this end, so it creates a bit of an angle. And what we're going to do is start with the cart at the top of the track here, let it go, and then watch it roll down. Now, the whole time the cart is moving, we can monitor the speed using the motion detector. And we can also measure the height of the cart off of the table using a meter stick. Now, just so you have a good sense of what we're doing here, I'm going to be measuring from the table to the letter R in the word vernier. That's printed on the side of the cart right here. So that's our reference point that we're going to use to measure the height. So the starting height of the cart is when it's up here at the top of the track. And so the height measured from the bottom, or measured from the table that is 7.4 centimeters, so that would be the starting height. And then down here, when it's at the bottom of the track, the height is 5.7 centimeters. Okay, so starting height 7.4, centimeters, and then final height 5.7 centimeters. So let's do the first run of the experiment. So the cart starts up here at the top of the ramp, and let's start collecting data from the motion detector, and then let go. Okay, now here's the data from the motion detector when we plot it out. The graph on the top shows you the position of the cart versus time. So position is on the vertical axis, time is on the horizontal. This graph on the bottom shows you velocity versus time, and that's the one we want to focus on for now. So the first thing to take note of is that the velocity is initially 0. That's before the cart started moving. But then after that, the cart steadily speeds up as it rolls down the track. Then, once it hits the side of the table at the bottom of the track, the velocity rapidly goes to 0. So what we want to do, if we're trying to find out what the final velocity of the cart was, is look at the highest point on the velocity versus time graph, or the maximum velocity that we see on this graph. And just by hovering the cursor over that point on the graph, we can see that the final velocity is 0.343 meters per second. So 0.343 meters per second is the final velocity for the first trial. Okay, for the next trial of the experiment, we're just going to make the ramp a little bit steeper. And so let's measure again the initial height of the cart from the table to the letter R on the label. And so that initial height, what I'm getting is 11.5 centimeters off the table for the initial height. 11.5 centimeters. And for the final height, that really hasn't changed. It's still 5.7 centimeters. And so once again, we'll collect data. We'll start with the cart at the top of the ramp, right up against the motion detector. We'll hit collect and let go. Okay, so let's take a look at the velocity versus time graph from that trial. So you see the same general pattern as before. We start at 0 velocity, we steadily increase until we reach the bottom of the ramp, at which point it rapidly dips to 0. So let's look for that peak on the velocity versus time graph. This time, it's happening at 0.920 meters per second. So the final velocity of the cart, when it's at the bottom of the ramp for this trial, is 0.920 meters per second. Okay, so for the last trial, we're just going to increase the steepness of the ramp even more. And let's measure the initial and the final height of the cart relative to the table. So when the cart is at the top of the ramp, its height relative to the table is 16.2 centimeters. And then when it's at the bottom of the ramp here, its height off the table is, so now it's 5.4 centimeters. Okay. So we'll collect data for the last trial. Again, start at the top of the ramp at the initial position, collect from the motion detector, then let go. Okay, and here's the velocity versus time graph for the third trial. Again, starting at 0 velocity, steadily increasing until we reach the bottom of the ramp. So the peak in velocity occurs at 1.299 meters per second. So the final velocity for the third trial is 1.299 meters per second. And so the last bit of data that we're going to need for this experiment is what is the mass of the cart that we've been using this whole time. So let's weigh it on the triple beam scale. We'll see what we get. So it looks like in order to get the scale to balance out, we have a cart mass of 271.5 grams. So 271.5 grams is the mass of the cart. Okay, so in this next experiment, we're going to be looking at how a bouncing ball loses energy over time. This is going to be apparent from the fact that the ball reaches a smaller height each time it bounces. So we're going to take a video of a bouncing ball right up against a meter stick. So each time it bounces, we can measure the height that it reaches. So starting at 1 meter, let's let the ball go and see what happens. Okay, so that's it for the lab. You've seen all the experiments and you've got all the data you need to do your analysis at home. So as usual, just follow along with the worksheet that accompanies this video and you should be able to do all that analysis. So that's it. I'll see you in the next lab video. Until then, be safe, be healthy out there. See you later.